Hello and welcome to my tutorial on surfaces and radiation. Today's learning objectives. Which surfaces are the best emitters of infrared radiation? Which surfaces are the best absorbers of infrared radiation? Which surfaces are the best reflectors of infrared radiation? And finally, what is meant by black body radiation? So, start your activity. Why do you think marathon runners wear foil blankets after the finishing line? So pause this video while you attempt to answer that question. And then when you're happy with your answer, press play. Right, well the answer is the blankets they are given help the athlete to regulate their body temperature. After a race, a runner's temperature will drop quite rapidly because they've ceased working their muscles. By the end of today's lesson, you should be able to explain how these blankets work. So, how does heat travel through space? Well, we know the Earth is warmed by heat from the sun, but there are no particles between the sun and the Earth. It's a vacuum. So the heat cannot travel by conduction or convection. So how does this heat travel from the sun to the Earth through space? Well, the answer is by infrared waves. Infrared waves are able to travel through a vacuum. So what is infrared radiation? Well, infrared radiation is part of the electromagnetic spectrum. It's a type of electromagnetic wave which transfers heat energy. So thermal heat energy is emitted from objects as infrared radiation. And you can find infrared radiation after microwaves, but before visible light. So again, what is infrared radiation? Well, all objects emit and absorb infrared radiation. Infrared radiation travels as waves in straight lines. The higher the temperature of an object, the more radiation it emits each second. The bigger the difference in temperature between an object and its surroundings, the faster this energy is transferred. So for example, if you had a very hot cup of tea in a cool room, that tea will cool down much more quickly. Why? Because there is a big difference between that hot tea and the room temperature. A body at a constant temperature emits radiation at the same rate that it absorbs it. And infrared radiation can travel through a vacuum at 300 million meters per second. It can be reflected and it can be absorbed. As infrared waves heat objects that absorb them, they are known as thermal radiation. So match each diagram in the top row of this table to its correct explanation below in the second row. Each one of these represents a body that's either absorbing or emitting radiation. The arrows travelling towards the body are showing infrared being absorbed. The arrows pointing away from that body show infrared radiation being emitted. So read the descriptions down below, pause your video and decide which explanation goes with each diagram. When you're happy with your answers, press play. Right, so your answer should have been A2, B3 and C1. And the reason for that is, with this first one, A, that body is going to increase in temperature because it's absorbing more infrared than it's emitting. Now for B, that body is decreasing in temperature. Why? Because it's emitting more radiation than it's absorbing. And then finally for C, that body's temperature remains constant. And that's because it's absorbing and emitting the same amount of infrared radiation. So we can see temperature through colour with a thermogram. Now, thermography uses cameras to detect infrared radiation given off by an object. In any thermogram, the brighter colours like red, orange and yellow indicate warmer temperatures, i.e. more heat and infrared radiation emitted, whilst the purples and the dark bluey blacks indicate temperatures which are cooler. In other words, less heat and infrared radiation being emitted. So if we were to compare these thermograms of a lion on the left and a polar bear on the right, the image of the lion shows that heat is released from most of the animal, excluding its thick mane. The eyes, the ears and the belly of the lion release the most heat and are therefore the brightest colours. In contrast, the polar bear's extremely thick fur and thick layer of fat provide excellent insulation, so most of its body is dark. Only the face is an area where heat is released. So you can see the brighter colours where the eyes and the mouth of the polar bear are. So you might carry out a practical similar to this. This practical is used to determine which surfaces are the best emitters of radiation. So to compare the radiation from two different surfaces, you can measure how fast two cans of hot water cool. The surface of one can is light and shiny, and the other is painted a dark matte black. At the start, the volume of water and the temperature of the water in each can must be the same, and the temperature is then recorded for both cans at regular intervals using a stopwatch. So, questions to consider. Why should the volume and temperature of the hot water be the same at the start? Which can will cool faster? Pause your video and try and answer those two questions. When you're happy with your answers, press play. So why should the temperature and volume of the water be the same at the start? Well, the bigger the difference in temperature between an object and its surroundings, the faster it will cool down. So if one can's water is of a higher temperature, the rate of cooling will be greater for that can. In terms of volume, a larger body of water will take longer to cool, even though it's losing heat faster. Simply due to the fact that there's more of it, it has more heat energy. So which can will cool faster? Well, the answer is the black or the dark matte surface. And the reason for this is because dark matte surfaces are the best emitters of infrared radiation. So your conclusion should be that dark matte surfaces are better at emitting radiation than light shiny surfaces. So if we took a photocopier, photocopiers use infrared radiation from a lamp to dry the ink on the paper. This prevents any smudging. So why does the black ink absorb more infrared radiation than the white paper? Well, the reason is as follows. A light shiny surface, like the paper, absorbs less radiation than a dark matte surface where the black ink is. This is because a matte surface has lots of cavities. You can see this matte surface here is this bumpy surface. You can see these cavities, these holes. So the cavities cause this infrared radiation to be reflected from the matte surface, but then hit the surface again. So you can see that some of the infrared may have been absorbed here, and then the infrared is scattered and it may be absorbed again here. So you can see that twice this infrared radiation has hit this matte surface. The radiation reflected from the shiny surface all travels away from the surface. So the shiny surface is going to absorb less and reflect more radiation than a matte surface would. So another experiment that you should do in class is where you use a Leslie cube, which is this thing here, to investigate which surfaces are the best emitters of infrared radiation. Now, a Leslie cube is a metal cube that can be filled with hot water. Immediately after filling the Leslie cube with hot water, the bung is placed in the top here, that's your bung. Each of the 4 vertical faces of the cube are painted a different colour. So one vertical face might be matte black, the other shiny black, white, or shiny silver. And then infrared sensors are used to compare the infrared radiation emitted from the 4 vertical faces. And the infrared sensor should always be placed opposite each face and at the same distance from that face. So for example, a fixed distance of 10 centimeters. These infrared sensors are connected to a computer, so usually a portable data logger that will record information continuously, and then this information can be transferred to a computer using a USB, and then graphs can be drawn for your data. So questions related to this Leslie cube practical. You might be asked, why is it important for the distance from the infrared sensor to the face to be the same? Well, the reason is infrared obeys the inverse square law. So the further you are from the emitter, the lower the intensity of the infrared radiation that will be detected by that sensor. If you move the infrared sensor closer to the cube, the reading would be higher. Moving it further away, that reading is lower. So distance will affect the results. And the only thing that you want affecting the results is the colour of that vertical face. So what are the advantages of using data logging equipment to collect the data in the investigation? Well, I said previously that data loggers are portable. I also said that they will record data continuously. But the main advantage is it's far more accurate because there's no likelihood of human error. So whereas humans might read equipment inaccurately or take too long to read or take a reading, or take a reading too soon, data loggers do it continuously and there is no human error involved. So your results will be much more accurate. Question 3, why was a bung inserted at the top of the cube immediately after the water is added? Well, the reason is A bung will limit energy loss through convection because particles can no longer escape through the top of the Leslie cube. So these are the model results. You could get results very similar to these. You can see that over here you've got the different surfaces of the Leslie cube. And here you can see the infrared radiation detected at 5-minute intervals. So at the beginning, at 0 minutes, then 5 minutes later, 10 minutes later, 15 minutes later. So you can see the interval size is 5 minutes. Now I want you to study those results carefully and decide which surface is the best emitter of infrared radiation. So if you think the answer is matte black, then you're correct. You can see that throughout, matte black emitted the highest levels of infrared radiation. So what is meant by black body radiation? Well, an object that absorbs all of the radiation that hits it is known as a perfect black body. A black body does not reflect or transmit any radiation. And since a good absorber is also a good emitter, a perfect black body which absorbs all of the radiation that hits it would be the best possible emitter. So a black body would absorb all of the infrared radiation and then it would emit that infrared radiation. So the radiation emitted by a perfect black body is called black body radiation. So a body that has constant temperature emits radiation across a continuous range of wavelengths. So the graph here shows how the intensity on the y-axis is affected by the wavelength of the black body radiation here on the x-axis. And you can see that two temperatures are given. You've got 750 degrees and you've got 1000 degrees C. So what conclusions can you draw from this graph? So you should be able to see that the intensity of the radiation is highest at wavelengths roughly between 2 and 3 micrometers. You can see that peak falls between 2 and 3 micrometers. But also you can see it depends on temperature. Can you see the peak is much higher for 1000 degrees C than 750 degrees C? And that's because when the temperature increases, the intensity of the radiation increases across all wavelengths. You can see for the higher temperature, the intensity is greater for all wavelengths. You can see that line for 1000 degrees C is always higher in terms of intensity than 750 degrees C. So see if you can attempt these higher tier questions. These are quite difficult. They're on infrared radiation. What I would like you to do is, whilst you attempt those questions, pause your video to give you time to answer them correctly. When you're happy with your answers, press play. So why is a perfect black body so interesting in terms of infrared radiation? Well, a perfect black body will absorb all infrared radiation that falls onto it without transmitting any or reflecting any of it. It is the best possible absorber and emitter of infrared. Explain why this filament bulb here emits more yellow-white light as it gets hotter. So you can see this animation here, you can see that as it gets hotter, more yellow-white light is emitted. Well, the reason is at lower temperatures, the filament emits longer wavelengths, red. And you can see on this diagram here that red has a longer wavelength. As that temperature increases, it emits wavelengths as shorter wavelengths, like the yellow here. You can see that's a shorter wavelength. So if you look at the bodies below, so you've got white, you've got orange, you've got yellow, and you've got red. Put them in order of hottest to coolest and explain your answer. Right, well, the hottest should have been white, followed by yellow, followed by orange, and then finally red, the coolest. And that's because hot objects emit more radiation at shorter wavelengths, and cold objects emit more radiation at longer wavelengths. So red would be the longest wavelength, followed by orange, then yellow. And you know, the hotter an object is, the hotter an object gets, the more radiation it emits across the entire spectrum, and the entire spectrum would give white light. So what I would like you to do, to see how much you've understood in this tutorial, I'd like you to attempt this true or false quiz. I'd like you to attempt those 12 questions. Press pause on the video whilst you're answering the questions, and only press play when you're ready to mark your questions. So question 1. Infrared radiation is an electromagnetic wave. That's true. All objects emit thermal radiation. That is also true, as long as they're above absolute zero, which is minus 273 degrees C. A small pan of boiling water contains more thermal energy than a huge iceberg. Well, that's false, because there are far more particles within that huge iceberg. If you don't understand that answer, please tune into my tutorial on the difference between heat and temperature. Right, question 4. The cooler an object is, the more infrared radiation it emits. Well, that's false as well, because it should be the hotter an object is, the more infrared radiation it emits. Question 5. The sun emits infrared radiation. True. Question 6. Dark matte surfaces are good absorbers of heat energy. True. Shiny silver surfaces are poor reflectors of heat energy. False. Because shiny silver surfaces are excellent reflectors of heat energy. Question 8. Infrared radiation travels in straight lines. That's true. Question 9. Infrared radiation can travel through a vacuum. That's also true. Question 10. Infrared radiation requires particles to travel. Well, the answer to that is false, because if it required particles to travel, it would never be able to travel through that vacuum, because that vacuum is an absence of particles. Question 11. A perfect black body is an object that absorbs all of the radiation that hits it. Well, that's true. And a perfect black body would be the worst emitter. Well, that doesn't make any sense at all. A perfect black body would be the best emitter. And the reason why it would be the best emitter is because it's also the best absorber. So all of the radiation it absorbs will be emitted. So if it's a best absorber, it will also be the best emitter. So the answer to our starter activity, can you explain how these blankets work? Well, hopefully you'll understand now that the runner's body is emitting infrared radiation, and a light shiny outer surface would emit much less radiation than a dark matte surface. And the shiny surface of the blanket actually reflects the infrared radiation back into the runner's body. So this means they actually cool down much more slowly. Now, if that runner would cool down very, very quickly, that could cause hypothermia. So by cooling down much more slowly, that prevents hypothermia. So thank you for listening to the tutorial. If you've got any questions, please add them to the comment box. Thank you.